Okay, we're moving right along. Now we're going to start discussing chapter 3 of the Bro book. I like to call this series of lectures Markov Chains and Infinity. And in chapter 3, what we're going to start looking at is what happens to a Markov process when time goes to infinity. And we're trying to, there's different things that could happen, and there's a more general case, which is everything's going to get mixed up and the random variable is going to stabilize to a certain distribution. But that's not always the case, and we need to be careful to figure out what conditions we need to meet that limit or that behavior at time goes to infinity. So we're going to start by in this lecture by introducing this idea of limiting distribution and making it precise. And throughout, I'm going to try to focus on two counterexamples and an example. I guess not necessarily the example, but on counterexamples where the limiting distribution or a limiting state where there's a well-defined distribution doesn't exist. Um, and throughout the lecture, you'll see that the language that we use is linear algebra, and mathematically, that's what we're going to be working with, linear algebra. So, and it's going to be all about the transition matrix. The next other lectures will go into more technical details, and we'll actually start discussing further properties of Markov chains that allow us to understand the behavior of the Markov chain. So now we are picking apart the Markov chain in more details, and we're going to try to understand it by understanding the transition matrix. So the transition matrix is getting to be the center stage, and we're trying to understand it through linear algebra. So this first lecture of the series, lecture 10, is going to be on the limiting distribution. All right, so let me start with an intuitive argument of this limiting distribution, and I'll start making things more precise. So here is my intuition. So I want to think of a Markov process as a random mixing process. In this case, I think of, for instance, a graph with some arrows and some edges, and I start in some state, and then I start flipping coins, and I go here, 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 and then after a long time, I'm just mixing in the different states. I'm just jumping randomly from state to state. So I'm thinking of it as a mixing process where the position where I am is kind of like being mixed. And in particular, one precise example to think about is shuffling cards. And in the example of shuffling cards, the states are the different order of the card configurations if you take in an order. So there would be like 15 to factorial different states with the different orders of the cards, which is a lot, but in any case, uh, it is finite and it's discrete, and you have all these states, and each time you shuffle a card, you go randomly from one state to the next. And the idea is that after shuffling the cards for a few, actually doesn't even have to be that long, but say an infinite amount of times, or like shuffling the cards for 100 times, then the cards are gonna be well mixed, and they're gonna be random, and there's not gonna be order. Each each time you do a simulation or of shuffling the cards 100 times, you're gonna get something different, and you should expect that each of the configurations should be equally likely. So after shuffling for a long time, you should expect that each possible configuration, each ordering of the cards is going to be equally likely because everything's well mixed, so nothing is more likely than anything, so it's going to be 1 over 52. So this is just a heuristic argument that you shouldn't be too hard to believe. You should trust me at this point, and we'll make this more precise. So this is what's happening for a Markov process. As time goes to infinity, things are getting really mixed, and after a while, we're gonna forget our initial conditions. So and that's what happens with shuffling cards. It doesn't matter how the cards were arranged initially. If you shuffle them enough, they're gonna be completely mixed, and it's gonna forget the initial conditions, the initial configuration of the cards. And mathematically, this is what this means. So we start our card shuffling with a specific order I, a specific state I, and then we are going to shuffle it T times. And we want to figure out the transition probability of starting with a certain configuration and shuffling the cards T time and seeing that we're in state J after T gets really large. And in here, this statement is saying, more specifically, that the transition probability for shuffling the cards a lot of times is going to be independent of the initial conditions. So you see that on the left-hand side, we have this initial conditions dependence, and on the right-hand side, it has disappeared. And essentially what's happening is we're forgetting the initial conditions. And this is in a large class of Markov processes, this is what's going to happen, but we got to make sure that we hit certain conditions. In the case of shuffling cards, it's a nice enough Markov process that things work out very nicely. So that's where we want to ground our intuition of a limiting distribution, where things are well mixed. And another difference from the shuffling card example to general examples is that the shuffling card example, all the in time as time goes to infinity, all configurations are going to be equally likely, and the probability of being in any configuration J is going to be 1 over 52. That won't be the case in the general case. The distribution, the limit could be different. So in here, we just say lambda J, and it just depends on the final state. So let's look at this more precisely. So this is a simple computation to kind of motivate the assumption before. So this transition probability, or an implication of this assumption, rather. So we're assuming the transition probability forgets the initial condition, and this is just the transition probability, and we want to see what the actual probability of the Markov process at time infinity is equal to. So time infinity, maybe we'll do this light green to represent the time infinity. So given this assumption that the transition probability is going to forget about the initial conditions, let's try to figure out what the distribution of the Markov process at time infinity is equal to. So just by definition, I should really just say that when I say x infinity equals j, the probability of that, really this is what I mean. I'm not deriving it, it's just notation here. Really, the left-hand side is really notation, and by this notation, really what I mean is this right-hand side. It's the probability of x sub t equals j as t goes to infinity, this limit. And here, to compute this limit, I use the law of total probability, law of total probability. I use the law of total probability to expand this as a sum, and I get this result with the conditional probability or the transition matrix for using the Markov matrix language. And I still keep the limit outside. I move the limit inside. I obtain this term in here. And this is now where I use the assumption from the previous slide, where I have that the transition probability is independent, forgets about the initial condition or is independent of the initial condition. So this term in the brackets is going to be equal to lambda j, as we denoted in the previous slide. And in here, note that the summation is from state I equals 1 to state n, and it's going to be the I dependence is going to not appear in this lambda j, so we can factor out the lambda j. And now, since this is the sum of this of the probability that x0 is a state I, and I is all the states, this adds up to 1. So we obtain that this is lambda j, which was equal to our transition probability. So we obtained that this transition probabilities are equal to the distribution of the Markov process at time infinity. And this is the interpretation that we have for this limiting distribution, this limiting Markov process as time goes to infinity. So by now, we're just assuming that we have this condition, that somehow, if we run the Markov process for a long time, the transition probabilities forget about the initial conditions because they're too far away. And the result is that this transition probabilities are going to give us the distribution of our Markov process at time equals to infinity. But we need to actually figure out when this condition is true. It's not necessarily true all the time. So let's define this, give it a definition. Since it's not necessarily true, it's not a consequence of just having a Markov process. We need to do more work. So let's take a Markov process x of t with a transition matrix P, and we're gonna define a limiting distribution to this probability vector, or which with entries lambda 1 through lambda n, which represent the probabilities of x infinity at states 1 through n. And we're going to call it a limiting distribution if it satisfies this identity, that the limit, we're doing limits t as t goes to infinity of this transition probability is equal to lambda j. And the question that we're trying to address and figure out is, do the limiting distributions always exist? Or how do we find the limiting distribution? Or what conditions do we need for the limiting distribution to exist? And it really boils down to asking the question of, do limits always exist? And you can already probably guess from your calculus class or your analysis class that limits don't always exist. And we got to be careful and make sure that we have the right conditions for limits to exist. So you might already guess that this limit is not going to always exist, and we need some conditions on our transition matrix to guarantee a limit. And this is what we're trying to figure out in this lecture. So in these cases of taking Markov processes to infinities, I like to focus on counterexamples. And I like to focus on the simplest counterexamples. And it turns out that these two counterexamples are essentially the only two counterexamples that are not going to give you a limit that exists. And we'll make this more precise in the next lecture, give a theorem. But for now, I just want us to understand when the limit doesn't exist. Because at the beginning of the lecture, we have this thought experiment or this Markov process heuristic argument for the shuffling cards, where in that sense it does make sense that a limit exists, but it's not always the case. And I want to always keep these two examples in mind. So the first counterexample is this Markov process, where if you start in state 1, you're just gonna and flip coins, you're just gonna keep coming back in state 1. And if you start in state 2 and keep flipping coins, you're just gonna stay in state 2. The transition matrix here is just going to be a diagonal matrix, 1, 1. And if we take the limit as t goes to infinity, and we see that we just get the limit does exist, and it's just the identity matrix, but we don't have a limiting distribution, because in here we see the transition between state 1 to 1 as t goes to infinity, and we see the transition from 2 to 1 as time goes to infinity, and we see that in here the transition matrix, the transition probabilities do remember the initial conditions. If you're coming from state 1, you're going to stay in state 1 with probability 1, and if you're coming from state 2, you're never going to go to state 1. So here, we don't have a limiting distribution because we do remember our initial conditions. So even though the limit does exist, we have to be careful because it's not that straightforward. We need to make sure that the initial conditions are forgotten. And this is not the case in this example. And in short, the reason that this example doesn't work out is because this Markov chain is not connected, meaning that you can't, there's no way that you can arrive to state 1 from state 2. And you can already start to think about how to generalize this property, not connected, for larger Markov chains. And we'll make this more precise in the next lecture. But this is the basic idea of how the limiting distribution may not exist, because a Markov chain may not be connected. Now, let's move on to the next example. And in this case, we're going to take basically the opposite of what we had in the previous counterexample, the other extreme. If we start in state 1, then when we flip a coin, we go to state 2 deterministically, and then in the next round, we go to state 1, and then we just keep switching states every single coin flip. The transition matrix here is now going to be 0, 1 and 1, 0. You can check for yourself. And if you square this matrix, take the two-step transition matrix, you see that it's 1, 0 or 1, 0, 0, 1 identity matrix. And if you keep doing this, you see that p to a t, the tth step transition matrix, it's either going to be p or p squared. And in here, so as t goes to infinity, the transition matrix is oscillating between p and p squared, meaning that at time, if you start at 1, at even times, if you start at 1 at time 0 at even times, you're going to stay in state 1, and at odd times, you're going to be in state 2. And this should be clear from the diagram and from the description of the Markov process. But in short, what's happening here is that here the limit does not exist because you're oscillating between two values. So you don't settle on a specific value. So these are the two basic counterexamples for limiting distributions not existing. And let's dive in a little bit deeper. So the idea here is that we're trying to take the limit of our transition matrix, and we want to make sure that in the limit, the rows are all equal to each other, meaning that so if we have, what's going to end up happening is that we want to forget about the initial conditions. So if we come from here and we want to exit here, over here, and this is going to be our transition matrix at infinity, we want it to be independent of where we arrive. So that means that if we arrive here, we should have the same value. So these two values should be equal to each other because we should be independent of the initial conditions. So the initial conditions are encoded by the row, and so we want that to be independent, and so these two values are going to be the same. So this is what we're trying to do. And in the question that we want to ask is, does there exist a limiting distribution? And we want to say we want to show first that the limit exists, and here I should have added that we additionally want the condition that limit t goes to infinity, p to a t, I1 to a j is equal to the limit as t goes to infinity, pt I2 j for every I1, I2. But the thing that I want to focus more is on the condition that the limit exists. We'll see this other property appear also. So to actually tackle this or think about this, so if I'm trying to compute this limit, p, I might as well just take the limit of the matrix, p to a t, instead of just the limit of the entries. It's going to be equivalent. And so this is what I do. I focus on the limit of the matrix, p to a t. And to take the limit of this matrix, the way to do it or make it easier is to diagonalize the matrix. So I write it as p times p is equal to u, d, u inverse, where d is a diagonal matrix with entries mu1, mu2, all the way to mu n. Then when we take the limit, we can actually diagonalize and then take the power t and then take the limit inside, and we obtain something like this. And in particular, we have that the limit is going to be equal to this. And it all depends on the limit of the diagonal. And one thing to note is that these diagonals, mu1, mu2, mu-n, these are going to be the eigenvalues of the matrix P. So now we're getting more into the technical part of it. So this is the limit. Is going to be really the limit of the diagonal term. And when we're taking the limit of this, the thing to note is that we're just taking the limit of each individual term. And we're going to have that as t goes to infinity, the only way for the limit to exist is for mu j to equal 1 or the absolute value to be less than or equal to 1. In this case, the limit as t goes to infinity will be 1, and in this case, the limit will be 0. So these are the only two limit points that we have for the diagonal elements. So this is one condition that we need for the diagonal elements, for the eigenvalues. And then to go one step further, let's try to think about what happens when mu1 equals mu2 equals 1. So when we have two eigenvalues that are equal to 1 where the limit exists. And in particular, we can think of the example that we thought we had earlier, where P was just the identity matrix and it's already diagonalized, so that mu1 here is 1 and mu2 is equal to 1. Then in this case, we have that if we take P goes to infinity, then we obtain the diagonal matrix again, 1, 1, and we have that the transition matrix remembers the initial configuration. So in this case, this is not going to fly if we have two entries that are equal to 1, two eigenvalues equal to 1. So in addition to this condition for the limit to exist, this is the conditions that we need for the limit to exist. And for the limiting distribution, we actually need a further constraint, which is that only one of the eigenvalues is equal to 1, and the rest of the eigenvalues are less than 1. So that means that only one eigenvalue is going to be equal to 1. This is true for only one j, and the rest of the j have to satisfy this. So these are going to be the conditions, the technical conditions that we need for the limit to exist and to obtain a limiting distribution. And this might seem, I mean, this is something concrete that you can check. You can put in your computer, you can have your transition matrix put in a computer and then find the eigenvalues. And then if you find these conditions, this is for one j, and this is for the rest. You can put this into the computer and see if your matrix P satisfies these conditions. And if it does, then you have a limiting distribution and you're done. But as you're aware, a lot of this theory was actually developed before computers were really that helpful. And people figure out other ways to characterize the type of matrix that satisfies these conditions. And this is an actually very beautiful part of this Markov matrices, of this Markov processes, that you can actually figure out that transition matrix has these properties by just looking at the entries, and you don't have to diagonalize anything. And you don't have to find the matrices U and U inverse. And that saves a lot of time, because imagine if you had to do that, you had to diagonalize the matrix P by hand, that would take forever. But we can actually find conditions that are easy to check without transforming the matrix that will lead us to these two conditions. And this is what we're gonna figure out in the rest of the chapter. But now that we saw how technically how the first counterexample fails, let's just take a second and see how the other counterexample fails. So in the other counterexample, we have this P, and which is the anti-diagonal ones, which corresponds to this diagram. And here we want to diagonalize this matrix P. We see that we can diagonalize it this way. And then when we take the teeth power, we're going to obtain this. And we see that this entry in the diagonal alternates between -1 and 1. And we see that the limit doesn't exist because this entry in the matrix is oscillating. So again, the limit does not exist because the limit along the diagonal doesn't exist. Now, let's start talking, before we move on to actually proving this conditions that will lead to limiting distributions. Let's just talk about more other objects for this transition matrix or other type of distributions or other results, and just get more of a feeling of this transition matrix and what happens. So I'm going to introduce this term of a stationary distribution. So a stationary distribution is going to be a probability vector, which is going to represent a probability distribution for a random variable x, which could be at any time. So you can think of it as the initial conditions. You can think of this as a distribution at time 0. And it's going to be the probability distribution for x0 for a Markov process. And we're going to call this distribution stationary if we apply P, the transition matrix, to the right of this distribution and obtain pi again. So in here is what's happening is we start at state I at some distribution pi I, and then we take one step with the Markov matrix, and then we stay in the same distribution. So this is saying that we're going to start with some distribution pi. With some distribution pi, we take one step with the Markov process, and we're going to remain the same distribution pi. So nothing's going to change after taking one step. You can think that essentially you're jumping back to the same spot, roughly. And the claim here is that limiting distributions imply stationary distributions, but not the other way around. We got to be careful about that. So this is giving another another interpretation of what it means to be a limiting distribution. It means that after an infinite amount of time, if you arrive at a limiting distribution and you keep applying the Markov chain or the transition matrix, your distribution is not going to change. You're just going to be stuck in that distribution. So this is another way to think of this limiting distributions, or more precise way, or further details on the limiting distributions. But as I mentioned in the previous slide, stationary does not imply limiting. And we go back to one of our favorite counterexamples. This one where you just jump back to your same state and your transition matrix is the identity. And here you can set pi to be a distribution, which you can think of it as the probability that x0 is equal to 1 and probability that x0 is equal to 2. So with this distribution, it's saying that we're starting at state 1 deterministically, and we're not starting at state 2. And here, when we apply the transition matrix from this to this, we apply the transition matrix to the distribution, and we apply the identity, we obtain 1, 0. So we recover the same distribution. So we see that here, pi is a stationary distribution, but as we've discussed earlier, this matrix does not have a limiting distribution because you remember your initial conditions. And just to have you think a bit more about this example, you should try to figure out if there's any other stationary distributions for this P. And here's a hint. There's going to be a lot of them. So try to come up with a few more stationary distributions that are different from this and see what you can get. But I'll leave that for you to figure out. So let me give you the proof of showing that the limiting distribution implies stationary distribution. So we start with a limiting distribution, lambda 1 through lambda n, and we show that it's stationary. So lambda j, by definition, is just the limit of this transition probability. Transition from I to j as t goes to infinity. And here, remember, it forgets about the initial conditions. So I just pick an arbitrary I. And since the limit is as t goes to infinity, we can actually shift time by +1, and we're going to still have the same limit. So the trick here in this proof is actually this shift of superscript, of the power of the transition. So instead of t, we're going to look at t + 1. So this is just shifting the time, but we're going to arrive at infinity regardless. And now that we've written as p to the power t + 1, we actually write it as the product of p to a t times p. And we have this matrix product. And I actually write that matrix product explicitly as the product of two matrices. And I still keep the limit outside. Then I take the limit inside. And I have the limit of this thing. This is independent of t, so it doesn't affect the limit. I can factor outside the limit. And I recall that this is my definition of lambda k. So I see that I substitute this with lambda k, and I see that I'm applying p, the transition matrix, to the distribution lambda k, and I recover the same distribution lambda j. And that's what it means to be stationary. So here, this is what it means to be stationary, and this is what we have here. And this is not much of a surprise. It should be an intuitive argument that if you're at infinity, if this is the limit at infinity, then this limit is going to be fixed, and it's going to be stationary. But this is the precise computation in the proof. Now, I'm going to wrap up this lecture by proving one more result. And this result, I like to think of it as just a reinterpretation of this limiting distribution, which is kind of consistent with what we've been talking about. And let me introduce this indicator functions, or this random variables jk, that are 1 if your Markov process is at state j at time k, and 0 otherwise. So this random variables are going to count the times that you are in state j. So for instance, if I take the sum j0 through jt minus 1, this is going to return the number of times I've been in state j in the Markov process from time 0 to time t minus 1. And then if you keep coming back to this state j, if you're in a case where somehow you're coming back to the same state over and over again, and you should expect this number as t goes to infinity to increase and go to infinity. But what we're interested in here is actually trying to take the average number of times that you are in a specific state as time goes to infinity. So we define this y sub t to be 1 over t times this sum, and this is the proportion of time that you are in state j. And the claim here is that if xt has a limiting distribution lambda, then the expected amount of proportion of time that you're in state j, the expected amount of time proportion of time that you're in state j is going to be equal to the limiting distribution lambda j. And this should not be surprising. First of all, we have that the lambda j's add up to 1, and the proportion of time should add up to 1, and it should be consistent with the distribution of your Markov process at time equals infinity. And this is an interpretation or a way that you can think about the limiting distribution. It really corresponds to if you're doing a random walk on, if you think of the limiting of a Markov process as doing a random walk in some graph, then the limiting distribution really corresponds to the distribution, the proportion of time that you spend in each state during this random walk. So we have this nice interpretation of the limiting distribution. And let me give you the proof. This is again a simple computation, and I'm actually going to, for concreteness, I'm going to assume that I start in some state I. We'll see that the result is going to be independent of I, but just for concreteness, I'm going to assume that I start in some state I, and I take the conditional expected value of yt given x0 is equal to I, by definition of yt, I just rewrite this, and with linearity, I take the summation and this factor out, and then I have this conditional expected value. And since this is an indicator function, jk, then this conditional expected value is just really this conditional probability. And now this conditional probability really is just the ij entry of the transition, the T transition matrix. So this is going to be P, K, I, J. And then we have that this limit is going to be equal to the infinite transition matrix, the infinite time transition matrix from I to j. And again, it forgets about the initial condition. It's going to be lambda j. Now, this limit may not be so clear or intuitive. So in here, I give a short idea of how to take this limit. And in particular, remember that this transition matrix for any ij is essentially, as k goes to infinity, as time goes to infinity, it's approaching a specific limit. And in particular, you can pick a cutoff time. I call it pink t. And after this time, this limit is going to be arbitrarily close to the limit alpha, or this transition probability is going to be arbitrarily close to alpha. So what I do is I take this summation here and I split it up into two parts. The terms before capital T and the terms after capital T. And in here, the first terms before capital T, I'm just going to say that this sum is some constant. It's some C, and I divide by T. And I don't care what it is. It's something ugly. It's just going to be the summation of this. And then for the terms after T, I'm arbitrarily close to alpha. So I can think of these terms to just all be equal to alpha. And there's going to be T minus T terms of them. And they're arbitrarily close to alpha. So this summation is going to be roughly this. And then this summation is roughly this. And here, this constant, this is just a constant. And when we take t goes to infinity, this is going to go to 0, this is going to be 1, and this is going to give me alpha. And this is how I obtain my result. So here, it's not being super rigorous, but this is the rough idea. And this somehow should be convincing of the result. And that's it. That's the end of this lecture. In the next lecture, we'll spend more time in going over more details and trying to prove the Perron-Frobenius theorem, which gives us the conditions of when the limiting distribution exists. And it's basically building up on the ideas that we've been developing in this lecture. So thanks for stopping by. I'll see you in the next lecture.